Okay, today's lesson is going to be on radioisotopes and radioactivity, as you can see from the title. Um, we've already looked at isotopes. We've seen many examples of some isotopes, and I'll just remind you of a couple of them. The other day we looked at something that would have been called a carbon 12, all right? Carbon 12 with an atomic number of 6, and a carbon 14, right, with, and again, atomic number of 6. And if we take a look at the particles in these two isotopes, here we've got, in terms of the number of protons, there's 6, and then the number of neutrons, remember we have to subtract, right, there's 6 as well. And in terms of electrons, and we're not really worried too much about electrons here in this particular lesson, there would also be 6, all right? But in this case, because we're talking about isotopes, remember, isotopes have the same number of protons but different number of neutrons. So if we take a look at this one, the number of protons, again, that is determined by the atomic number, 6. And if we take that 14 and we subtract 6, then the number of neutrons is 8. So here we have two different isotopes of carbon, one with 6 neutrons and one with 8 neutrons. All right, and that makes them isotopes. Now, I guess the question is, what is a radioisotope? And you've probably heard of radioactivity before as well. And at this point in the lesson, if I were here, I would ask you students what you think of when you hear the term radioactivity, right? And I get lots of interesting answers. People talk about fish with 2 heads and all kinds of, and radiation, right? And emissions and things like that. And obviously we also get terms like cancer, right? Because you're all aware that radiation and radioactivity can be cancer causing, all right? Some people even come up with things like treating cancer, right? If somebody has a radiation therapy, they'll be using radiation to treat, cancer. So those are all good things, except like the 2-headed fish. That's a very rare scenario. But anyway, let's talk about what causes this radioactivity and what radioactivity really is, and how that relates to this thing that we call radioisotopes. All right, so let's jump ahead here and let's put some definitions down. Again, I'm going to go quickly so you can go back and write the note from the PowerPoint presentation. We already know that many elements have 1 or more isotopes, but in this case, what we're saying is some of these isotopes are unstable, all right? Atoms of an unstable isotope decay, emitting radiation as their nucleus changes. And we do use the term decay here, but the term decay is not like you might have learned in, say, an ecology class about like a log decaying in the forest. That is not what we mean by decay here. The term decay is used here because of the mathematical way in which the radiation decreases, and I will show you examples of that later on, all right? So we say that the isotopes decay, but they're not like getting old and breaking down. They're just changing, all right? And they change by emitting radiation as their nucleus changes, all right? So if an isotope can decay, if it's unstable, as I said up here, then we call it a radioisotope, and we say that they're radioactive, all right? So those are the terms we use. So let's write a little bit of information down about alpha particles. Again, when you run through the PowerPoint, you'll have a chance to write these down. They're helium nucleuses. This doesn't say he, like a boy, He, helium. Therefore, they're made up of 2 protons and 2 neutrons. And so if we have the symbol for them, it looks like this, He, mass number 4, atomic number 2, right? 2 protons, 2 neutrons. And why would a radioactive element give off an alpha particle? Well, it turns out that if an element has too many protons, all right, when it comes to the nucleus, a nucleus is most stable when it has approximately the same number of protons and neutrons. And it likes them in pairs. I can't explain to you why. To be honest, I really don't know exactly why. I've read some stuff on it, but let's just say that when they've got similar numbers of protons and neutrons, they're stable. So if we take a look at something like uranium, an atomic number of 92 protons, and a mass number of 238, it doesn't take a quick subtraction of approximately 100 to realize that, we've got about 130, 140 neutrons in here compared to 92 protons. That's an unstable situation. So what does an unstable uranium do? It spits out an alpha particle, all right? And now let's figure out what's left here, all right? So when we figure out, or when we do a calculation involving a nuclear reaction, it's really easy to figure out what you got left because we need to have the same mass at the end, in other words, the conservation of mass. So if I've got a mass of 4 removed from this mass of 238, I'm going to end up with 234. And if I have a charge of 2 protons removed from a nucleus that has 92, then I'm going to have 90. And now we can go to our periodic table. So if I take a look over here, I'm looking down here at my uranium. There it is right there. Now I've lost 2 protons, 1, 2. I'm to 90. That is a thorium, which means I have here a thorium. All right? So that's a simple way to balance a nuclear reaction. That's an example of an alpha decay. It literally spits out a little chunk of its nucleus, and a new nucleus is left, all right? So the atom literally changes into a new type of atom with a little piece flying out. And it's this piece flying out that's the dangerous part, right? These little pieces can run into other atoms and cause them to knock out some electrons, or maybe even knock out some protons and neutrons and change those atoms. And if those atoms happen to be in the DNA of a cell, those atoms changed in the DNA could cause a bad mutation, a bad change, and that can cause cancer. So that's how these radioactive particles do their damage. They can run into atoms in the DNA of a cell and cause trouble, all right? So that's an alpha decay. Let's take a look at beta. All right, so beta particles. Beta particles are negatively or positively charged electrons. And yes, you heard me right. This is probably the first time you heard of this. Positively charged electrons. The positively charged electrons are called positrons, and I'll talk a little bit about positrons in a moment. So here we have a symbol representing an electron. We're going to write it as if we're writing an atomic notation. So an electron isn't really an atom, but we can write its symbol down, E, and it doesn't really have protons, but it has a negative charge. So in the place of atomic number, instead of writing down the protons, because there isn't any, we can write down the charge. So really, let's think of this bottom number now as thinking of the charge number instead of the atomic number. So we now have a charge number of -1. The electron is really light. Remember, it's like 1/2000th of a proton. So it essentially has a mass of 0. So we represent an electron with an atomic number, right? Essentially, its charge number, -1, and a mass number of 0. And if we're talking about this strange positively charged electron, it has a charge of +1 and a mass of 0, all right? And I'll talk a little bit more about these two guys in a second. Let's take a look at an example of where a beta particle can result. So if we take a look at this hydrogen with 3 mass, right, 1 proton. So it's got 2 neutrons and 1 proton. It's got more neutrons than protons. Remember, I just said atoms are the most stable when they've got about the same. So this is unstable because this hydrogen atom has 2 neutrons to 1 proton. So what it will do is it will eject a beta particle. It will eject an electron right from the nucleus, which is also a strange idea. We thought electrons only existed in orbit, but they can actually be ejected from the nucleus. If we do the math, 3, 0, I need the mass to be the same as it was at the beginning. So the mass is still 3. Charge, and my charge has to be conserved as well. It can't just disappear. So if I've got +1 on the left, and then I've got a -1 here. Whoops, I didn't mean to write that. I was just circling. If I got a +1 on the left and a -1 here, what do I have to put here to get a number of +1? Well, I need 2, because 2 plus -1 is 1. So what atom does that get me? Well, now I need to look up my atom that has an atomic number of 2, and you'll take a look here, atomic number of 2, helium, there it is there. So let's switch back here. So that's, and I'm going to lose my writing for some reason. There it is. And that turns that into a helium. Okay, so let's think about what happened here. Whoops, it's terrible E. In this case, what happened? The neutron spit out a little negative chunk and turned into a proton. There's that little negative chunk. So that is a beta emission, okay? Let's take a look at one that produces this positively charged electron. Okay, move on to the next one. Oops, come on, computer, behave. All right, so let's take a look at this one. In this case, we've got beryllium, mass number 7, atomic number 4, 4 protons, 3 neutrons, more protons than neutrons. Again, unstable. So let's take a look. In this case, a positive chunk, let's put a little positive there, is going to be emitted. Again, 7, 0, 7. 4 plus 1, it has to add up to 4. I need a 3. A little look at what we're dealing with here. 3 means I have a lithium. Okay, so the beryllium has been turned into a lithium. So what happened here? In this case, too many protons. A proton spit out its little positive chunk, like it spit out its positive piece, therefore turning it into a neutral particle like a neutron. So in this case, a proton became a neutron when a positron was emitted. The last type of radiation is what we call gamma radiation, and that's that last one. Now, gamma radiation is not a particle. Gamma radiation is a type of electromagnetic radiation, which is essentially light. All right? It's really high energy light. High energy. All right? It's very, very penetrating. It's like the nucleus is readjusting the positions of all the pieces so everything can get a little more closer. And when it does, it gives off a burst of gamma radiation. All right? So there is the third type of radiation. No equation needs to be done because the nucleus doesn't turn into something new. Okay, where am I at? There's some information about the way the nucleus, or sorry, the types of radiation work. So here, they're relatively slow, but they're heavy, the alpha particles. They can only go a few centimeters in air until they run into some air particles and stop. And a piece of paper would stop alpha particles. Really, you can stop an alpha particle pretty easily. Beta particles go relatively fast. They're faster. They can go a few meters in the air until they run into some other atoms. And 1 or 2 millimeters of metal will stop them. But gamma radiation is incredibly penetrating. Very fast, speed of light, penetration in air, can go right through air. And it takes about a meter of lead or concrete to stop them. And that's why our nuclear power plants are built inside these great big concrete domes to keep the gamma radiation from getting out.